Hello everyone, I'm Sahar from Center for Advanced Modeling and Geospatial Information Systems CAM-GIS at UTS. And on behalf of the team, I'm presenting a project titled Using Deep Learning for Meteorological Drought Forecasting for New South Wales, Australia. Droughts are one of the environmental hazards that affect large number of people each year, and they are also highly costly. As you can see, just in 2015, about 25 million people around the world were affected by drought and has costed about 300 million US dollars. Droughts are amongst the most complex environmental hazards, and they have been recognized as the least understood amongst all weather and climate extremes. Therefore, there is no uniform definition for drought. But drought has been classified into meteorological, agricultural, and hydrological. These categories are based on the drought impact on a specific sector, considering the intensity, duration, and the spatial extent. For example, as it's shown, short-term drought in a small area affect the weather. But for example, the decade-long drought contributes to widespread crop failures and therefore called agricultural. Hydrological drought occurs when low water supply becomes evident after a long time of meteorological drought. Droughts are not preventable, but they're predictable, and therefore developing an early warning system is possible to be prepared for an upcoming drought event. Actually, modern agricultural enterprises need to prepare themselves as best they can for the potential impacts to minimize the cost of drought. In order to predict the drought in the future, a minimum of 30 years of meteorological or climate data is required. The amount of time that the drought can be predicted in the future is called lead time. The longer the lead time, the better we can be prepared for mitigating the drought impact. However, predicting the drought and particularly predicting it in a longer lead time is very challenging because droughts are non-linear in nature and they can be affected by the combination of different meteorological, climatic, and hydrological factors. On the other hand, in order to focus at higher lead times, we need to consider the climatic variables. This becomes even more important as the study shows that the climatic variables and droughts are highly related in Australia. We should also consider that the climatic factors don't affect drought immediately. For example, the big changes in the sea surface temperature at a certain time may cause the drought a few months later. That's why we say these variables affect drought at the lag time, which increases the complexity of forecasting drought. So both choosing the right prediction method and the factors, or let's say the right data, is very important. Different machine learning methods has been used to predict drought. Artificial neural networks are amongst the most popular and effective data-driven methods, and they have been extensively used in the past decade and proven to be effective tools for forecasting at short and long lead times. But despite obtaining satisfactory forecasting results, neural networks are incapable of dealing with time series in drought estimation and suffer from overfitting due to lag component in the drought prediction that I mentioned before. Therefore, considering the amount of the data for drought prediction and also the complexity of the system, deep learning methods, especially long short-term memory or LSTM, seems to be an efficient method for predicting the drought. LSTM is capable of retaining information for longer periods due to its recurrent and gate architecture. About the data, drought indicators indices are most commonly used to identify droughts. For example, a standardized precipitation evaporation index or SPI is one of these indices. SPI has the ability to utilize both rainfall and temperature. The use of LSTM in drought forecasting is still in its infancy. with the majority of the studies focusing on forecasting drought variables such as rainfall, sea surface temperature, or SST, evaporation, and so on. Therefore, we use LSTM for predicting the SPEI index. The present study actually is the first one to focus the drought index by using a stack LSTM architecture at different lead times. As you can see, the monthly data from 1902 to 2000 was used for training, and the data from 2000 to 2018 was used for testing. Here is the architecture of the stack LSTM that we use. The stacked LSTM is an extension to this model that has multiple hidden LSTM layers where each layer contains multiple memory cells. So therefore, we first compare three different machine learning methods: support vector machine, random forest, and artificial neural networks, along with LSTM to focus at the lead time of just 1 month. And then we improve our study to focus at higher lead time, up to 12 months. The result of the LSTM method was compared to the result from using ANN, SVM, and RF. As you can see, LSTM outperforms the other methods, so we decided to use this method to predict the drought in different lead times. You can see the comparison of the observed and forecasted SPI values at different instances with lead times of 1 month, 3 months, 6 months, and 12 months. And it's shown, the accuracy drops and the RMSE increases as we try to predict the SPI in the higher lead times. By predicting the SPI, we can find information about the important characteristic of the drought, such as the beginning of the drought, the end time of the drought, the drought duration, the drought intensity, the drought severity, and the drought categories. And also, the drought extension, special extension, which is the affected area. Actually, the lower the SPI in an area, the more severe the drought would be in that area. So in this study, we compared the observed and predicted SPI value in NSW in different lead times. We identified drought intensity, drought duration, and the number of drought months considering the predicted SPI values. We calculated the threat score, TS, which measures the fraction of correctly predicted results corresponding to the observed values. In this study, we concluded that LSTM model was able to better forecast meteorological droughts at lead times up to 12 months, with the threat score ranges between 93% for 1 month lead time and 78% for 12 month lead time. We also concluded that the influence of climatic variables greatly affect the forecasting results at higher lead times. For predicting at higher lead time, for example, 18 months, the performance of other architectures such as CNN, LSTM need to be investigated. More details about this project can be found in these two papers. They have been recently published in Q1 journals. Thank you.